Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Now, as a space and astronomy news program, we don't generally have to worry about relaying too much depressing news. There's the occasional exploded rocket or satellite that misses an orbit, but except for the thankfully rare loss of life among astronauts, what we talk about is fairly upbeat. But then there are days like today when we're reminded that Earth is a planet. And as we cover our own world from a scientific standpoint, things aren't always that great. In the past, we've talked about planet obscuring dust storms on Mars, and now we have Earth images from the NOAA 20 spacecraft depicting continent obscuring dust here on Earth. Those of you living in Europe may already know from your weather forecasts that a massive dust plume stirred up across northern Africa is now sending dust out over the Atlantic Ocean and northward toward Europe. The wider perspective that we can get from the Discover satellite shows more of that dust as a beige cloud sweeping off the African continent.
While the images are eerily beautiful and make for neat comparative science between Earth and Mars, they point to a more human tragedy. In southern France, the air is dense with fine particulates and the sky is beige from the dust blocking out the sky. This dust is significantly more intense than past dust storms, and this doesn't bode well for folks living at the base of the Alps. This dust, as it settles out of the air, coats everything, including the snow, which will then melt more readily and melt earlier in the season. In the past, these kinds of dust plumes have even carried microbes from the Sahara to the glaciers of the Alps. According to the Barcelona Dust Forecast Center, this weekend, Saharan dust is expected over the Iberian Peninsula and Western Mediterranean. Looking at these forecasts, I'm kind of glad that wearing masks is becoming more normalized. This isn't something you want in your lungs, and unfortunately, these kind of dust events are likely to also become the new normal.
As our planet's carbon dioxide levels rise, and with it the temperatures, we're seeing the oceans and land are driving winds in new ways. In Texas, these changes led to a massive Arctic blast last week as the jet stream failed to trap the Arctic cold in the Arctic. New research from Jordan Abel that appears in the journal Nature tries to understand just how the winds are changing by studying what the Earth was like last time the CO2 and temperatures were this high. That last time, it was the Pliocene epoch, 3 million years ago. That time when early hominids were emerging and giant mammals still wandered the Earth. Looking at the geologic record to see where the wind carried dust during that time period, this research team discovered that Earth's westerly trade winds migrate more northward as the temperatures warm. There's no way to know on what time scale things will change, but over time, perhaps centuries, maybe less, this change in wind will mean less rain for North America, Europe, parts of Australia, and New Zealand. Where things grow will change and deserts will migrate. This has happened before. But this is the first time such change has been so rapid. And the next question becomes, can life adapt quickly enough to the changes that are coming?
Changes in rainfall and winds are just some of the factors that affect forecasts for fire season. New research from Stephen Bray and company appearing in Earth's Future indicate that figuring out just where fires are likely to break out and how widespread they can become is more complicated than anyone would like. The primary indicator of if it will be a bad fire year is the vapor pressure deficit. This is the difference between how much moisture is in the air and how much moisture could be in the air if it were saturated. While dry air generically lends to more fire, the devil is in the details, and those details include precipitation, evaporation, relative humidity, zone soil moisture, and wind speed. In trying to understand how widespread fires will be in the future, this team concludes, and here I quote from the paper: We show that increases in burn area are likely as many climate models suggest the future will be drier. However, we find that future wildfire burn area estimates are lower whenever and wherever the importance of aridity is reduced. Put another way, if we let our land dry and see a reduction in plant life and agriculture, more will burn. If we want to offset the effects of climate change, we need to find ways to maintain soil moisture as rains recede.
Unfortunately, climate change doesn't affect just the landscape. It also has a huge impact on life in cities. And unfortunately, studies are finding that how someone is affected is strongly biased by an area's poverty levels, and those generally reflect racial divides. In trying to mitigate the worst effects of climate change, the United Nations has devised a series of global goals that should both improve quality of life and improve our world's future. A new study looks at how we're doing along three of these goals, which include providing everyone with access to affordable public transit, providing adequate waste management systems, and green spaces accessible to all. To measure what is actually going on as we try to achieve these goals, researchers combined data from OpenStreetMap to tell them about transport and used satellite data to study green spaces and waste management. By combining this data with demographic information, it became possible to understand where problems may arise. And the answer was everywhere. No city over 10 million had equal access to people of all demographics, and very few smaller cities scored highly in both environmental performance and inclusivity. Those few exceptions included Freetown, Sierra Leone, Darwin, Australia, and San Jose, California. To quote from a summary of this research prepared by EOS, more than half of the 164 largest cities fell into the category of good overall performance, but with lower income neighborhoods bearing a disproportionate share of environmental burdens. Reasons for these inequalities are linked with local contexts. In inner city communities, air pollution is often worse, and a lack of tree cover and green space can result in dangerously high summer temperatures through the urban island heat effect. Essentially, as too often happens, the worst effects will be lived by those least able to afford to find solutions. As a global civilization, we need to do better to ensure we provide all humans an equal chance to at least have a cool green space to escape to. We'll include links to the full data set on our website, dailyspace.org. After the break, we'll be back with some better news, including how the impacts of wild dingoes can be seen from space, and how dark matter just might play a role in forming supermassive black holes.
Dingoes, those scruffy wild dogs of the Australian outback, usually portrayed as a nuisance. Turns out they're good for the ecosystem, according to a new study from the University of New South Wales, Sydney. The study, published in Landscape Ecology, looked at 32 years of satellite data from NASA and the United States Geological Survey's Landsat program. Previous dingo research has been site-based or relied on drone imagery. This satellite data has made landscape-wide analysis possible for the first time, and it revealed something very interesting. A time-lapse video of satellite images posted on the university's YouTube channel reveals a pronounced straight line along the New South Wales state border, where a large part of the dingo fence runs. Vegetation inside the fence, where there are no dingoes, had poorer long-term growth than vegetation in area with dingoes. The dingo fence was built in the 1880s to protect livestock. It spans parts of Queensland, New South Wales, and South Australia, and at 5,600 kilometers long, it's one of the largest structures in the world and has been extremely successful at keeping these dingoes out. But while this might keep livestock and other fauna from getting chomped on by hungry dingoes, it's not so great for the local flora. In this data compilation, we can see the long-term effects of removing dingoes from the local ecosystem. And we can see those long-term effects from space. That's right. The environmental impact of removing dingoes is visible from space. The Great Wall of China isn't even visible from space. Professor Mike Letnick, senior author of the study and a researcher at the university's Center for Ecosystem Science, said in an interview, when dingoes are removed, kangaroo numbers increase, which can lead to overgrazing. This has follow on effects to the entire ecosystem. Those follow on effects are a process called trophic cascade, which in this case means fewer dingoes led to an increase in kangaroo populations, which leads to overgrazing, which reduces vegetation and damages the quality of the soil, which causes even less vegetation, which hinders the survival of smaller animals. This goes to show how precariously connected everything on our planet is. According to Professor Letnick, the fence's sharp divide between dingo and non dingo areas provides a rare opportunity to observe the indirect role of an apex predator and the far reaching effects of removing apex predators from an ecosystem. And this was all made possible by satellite data. Satellite imagery usually only looks at photosynthesizing vegetation, meaning plant life that's visibly green. But the university researchers used a model to factor in non green vegetation, such as shrubs, dry grasses, twigs, branches, and leaf litter, stuff that's important to a desert ecosystem like the one found in the Australian outback. The model was developed by the Joint Remote Sensing Research Program, a collaborative group that includes the University of New South Wales. According to lead author Dr. Adrian Fisher, a remote sensing specialist, there were other contributing factors to the difference in vegetation, such as differing rainfall patterns and land use, but the dingoes definitely played a central role. Dr. Fisher went on to say, our study is an example of how satellite technology can be used in big picture environmental research, and they hope to next use the Landsat images, which are freely available for download, to study how different amounts of vegetation can influence bushfire frequency. While this dingo study can be seen as yet another example of how human made structures are negatively impacting the planet, it also shows that even some scruffy wild dogs can play an important role in making the earth better for everyone. We'll be back after this break with that whole black hole, supermassive beginning of the universe story. Be right back.
All right. The next story isn't as cheerful as dingoes making for a healthy ecosystem, but it's still a pretty cool mystery that may be solved. One of the issues astronomy is currently scratching its head over is how the universe formed massive galaxies so fast. For the first roughly 400,000 years, everything was a hot, dense soup of colliding photons, electrons, and atomic nuclei with other particles that were all together expanding and cooling, but were too dense and too hot to form atoms, let alone galaxies. One day, though, things did get cold enough to form atoms. That was about year 400,000, give or take, but things were still too hot for everything else. And the universe just kept expanding and cooling, and we expected that stuff would start forming a few 100 million years later. But somehow we are finding, as we build bigger and better telescopes, galaxies weren't so much starting to form, they were fully formed. And this is deeply confusing. Here's the problem. Our universe is mostly empty space. With the modern universe, we see all sorts of big structures that shine in the sky. And all that stuff in those structures was initially spread out pretty much uniformly. And it should have taken time for material to gravitationally come together. The luminous stuff, the luminous matter, baryonic matter, isn't the primary stuff of the universe, however. There's also dark matter, stuff that, as the name implies, refuses to interact with light. It is a whole lot more prevalent, and as we've realized, galaxies formed early. Astronomers built theories for how massive clouds of dark matter could come together early in the universe and pull in the regular matter to start galaxies earlier. This helped, but It still didn't explain how these galaxies somehow came together early in the universe and had supermassive black holes in their centers so fast. So the new question became, can you make a supermassive black hole out of dark matter? It's just stuff, after all. There shouldn't be a reason it can't make a black hole, but it's just a matter of how would that work? Dark matter, as far as we know, consists of particles that don't like to interact with each other or anything else, including the electromagnetic spectrum and force. The question becomes, if you pull enough dark matter into a small enough region, will it tend to collapse under gravity or will it support itself through gas pressure of some sort? This is sort of like asking, will air in a cooling room keep filling the room or collapse and condense on the floor? Eventually, it will collapse, but not at a temperature we're going to get on Earth. Turns out, however, the dark matter may collapse into black holes under the conditions that existed in the early universe. In a new paper appearing in monthly notices of the Royal Astronomical Society with lead author Carlos Aguirreras, researchers examine what conditions need to occur for dark matter to collapse into a supermassive black hole. They find that the answer depends on just how big dark matter particles may be. For particles in the tera-electron volt range, the size of neutrinos, for instance, a sphere of 1 billion solar masses can collapse under its own gravity to form a supermassive black hole as early as 500 million years after the Big Bang. Bigger masses, they could form even earlier. And this is consistent with what we're seeing. It's kind of weird to think that an invisible component of our universe, dark matter, can form massive halos that collapse into supermassive black holes that are also invisible but shape everything in the galaxies that grow around them. In our universe, the brightest shining things are truly being governed by invisible hands, or at least the gravity from invisible sources. This is also a case of both and. We originally thought supermassive black holes formed through the more gradual buildup of regular matter inside clouds. That still happens. That just happens more slowly. Our universe found a way to fast track the creation of galaxies, proving once again that there are often many ways to do things, and the universe doesn't like to be limited in its options. It does things its way. After the break, we're going to take a look at some of the faces who need to be remembered year round as Black History Month comes to an end. Stay tuned.
Here in the United States, February is designated as Black History Month. During this month, many people and organizations make a point of celebrating the oft-times overlooked contributions of Black Americans to a variety of fields, including the sciences. No list we create will ever be comprehensive enough to cover all of the amazing people whose names we should know, alongside Einstein and Hawking and Sagan. But that doesn't mean we shouldn't try. I acknowledge that as a white woman, my position in this country comes with a lot of privilege. I'm going to use that position to help make the following names and accomplishments better known. Benjamin Banneker was a free Black American mathematician, author, surveyor, landowner, and farmer, considered to be the first Black astronomer in the United States. He worked as an assistant surveyor with Andrew Ellicott, mapping the lands and creating the boundaries for the new federal capital in Washington, D.C. Arthur B. C. Walker Jr. was an African American physicist who studied the sun's atmosphere in both ultraviolet and X rays. He later developed and tested the X ray mirror technology that is now used in the SOHO spacecraft. In 1986, he chaired the committee that investigated the Challenger space shuttle disaster. George Carruthers was an inventor, physicist, engineer, and space scientist. He perfected an ultraviolet camera spectrograph for NASA to use when it launched Apollo 16. Claudia Alexander was a research scientist who specialized in geophysics and planetary science. She worked for the U.S. Geological Survey and NASA's Jet Propulsion Laboratory on missions that included Galileo, Jupiter, and Rosetta. Beth A. Brown was a NASA astrophysicist who specialized in the study of black holes and the emission of X ray radiation from galaxies. In her work at NASA's Goddard Space Flight Center, she championed science communications and higher education. Again, these are but a few people we think you should know. We will include links to full biographies as well as more lists of amazing Black Americans in our show notes. As a final note, earlier today, NASA renamed the NASA headquarters building in Washington, D.C. in honor of hidden figure Mary W. Jackson. Jackson was the first African American female engineer at NASA and began her career with the agency in the segregated West Area Computing Unit of NASA's Langley Research Center in Hampton, Virginia. She posthumously received the Congressional Gold Medal in 2019. This has been The Daily Space.
See you all next week. Thank you.